now, but he remains somebody deeply interested in mathematics and mathematical physics. And he's going to be telling us today about the relationship between gauge theory, physics, economics, and other things.
Thank you. So,
and if you want a pointer, welcome to Canada.
Thank you very much. So the topic today that I'm going to try to address is going to have at its core gauge theory of markets. And many of you have probably seen at some point in your life one of these talks where somebody from the psychology department or an operations research department attempts to convince you that something that you know well, that is very beautiful, has tremendous application. And very often, you're left feeling that either the example is tortured, that somebody is trying to fit a round peg into an oval hole. And what I'm hoping today is that you will apply a higher standard to what it is that I'm going to show you. I would like to show you an application of gauge theory on par to the naturality of gauge theory, fiber bundles, and connections in mathematics and physics. So the point for physics will be, what is the implication if a system which is not God-given, like a market, lends itself to a description by such a structure that we have commonly associated with perfect or near-perfect systems. So the inflation will not be a cosmological theory, but will be inflation that we're familiar with from the markets. So let's begin with where I think a lot of this mysticism started, which is a beautiful paper by Eugene Wigner, in which probably the most beautiful part of the paper is the title. Why is it that pi and e and Gaussian distributions find themselves far outside of the realms in which they were originally developed to solve problems? So Wigner said, and I quote here, that the miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. It's a beautiful sentiment. I may take issue with it. But he clearly saw that it was possible that this unreasonable effectiveness might lend itself far outside of fundamental physics, even though the unification of gravity and the other forces was clearly in his mind in that paper. Around 1975, something interesting happened at Stony Brook. This was the discovery of the Wu-Yang dictionary. Now, I tried to do a little bit of research on this, and I was stunned that there's very little that is Googleable. Somehow this topic has faded from memory. So this is the Wu-Yang dictionary, and if memory serves, James Simons of the math department was invited to give lunch seminars to some of the physicists. And something weird happened in the cafeteria down there, because what they found was that there was a complete correspondence between concepts that had originated in one field with concepts that had originated in another. And it was quite striking. And mysteriously, shortly after this, James Simons disappears from mathematics and shows up as a billionaire on Long Island. So it is possible that some of the discoveries, that as much as I would like to associate them with myself and my collaborator and wife, Pia Milani, it may be that somebody else has seen this before, and more successfully. So what did Wu and Yang add to this mix? Well, they said it is a widely held view among mathematicians that the fiber bundle is a natural geometric concept. Since gauge fields, including in particular electromagnetic field or fiber bundles, all gauge fields are thus based on geometry. And the underlined sentence which followed begins the kind of thinking that we have all either accepted or resisted, which is that some sort of a miracle is going on, in that the perfect sense, the sense of perfect modeling, where what we are trying to model in physics is exactly captured by some structure introduced for its own beauty in mathematics. This suggests that if we look at these curvature equations, either linear in the curvature or taking a derivative of the curvature, that somehow we are capturing a tremendous amount of the natural world by simply finding equations that we see nowhere else and using them to model all of the interactions that we believe to govern our world. Is there anything comparable in economics? Well, no. Things are terrible in economics from many perspectives and wonderful from many others. But let's look at the case of hyperinflation. Right? This is something that's had a huge impact on our world. Think about Germany during the early 20s and what happened afterwards. It's probably worthwhile developing a very good tool to measure inflation. The index number problem has to do with the fact that many economists have introduced methods of measuring inflation which are not compatible. So the names most typically associated are Laspers and Pasch, who got in on the ground floor. Laspers index, let's see, this is a price index. What it does, so let me just, in what follows, we are going to consider goods and services as modeled by an n-dimensional vector space V over the real. So implicitly, that means that we are going to have units for each good, and we are going to be able to get down to fractional amounts of those goods to the point where a continuum makes sense for modeling the goods. So Q will always be a basket of goods and services. And in some cases, we'll want to take Q to have negative components. For example, when we're looking at currency trading, if I go long one currency, I go short another currency. I gain one currency by taking on debt somewhere else. In many cases, we'll be simply looking at the positive orthant, or the positive quadrant, whatever we want to call it, of the vector space. Conversely, if I have a unit such as the dollar, Canadian, and I attempt to evaluate the price of that basket at any given time, what I have is a covector, although maybe the economists don't frequently say it that way. The value of P on Q is simply the inner product given from the vector space, dual vector space relationship. And that's valued in your unit of currency. So what these are vector relationships in components. And the Pasch and the Laspers are the comparison of two covectors of prices using either a reference vector from the original time, in the case of the Laspers index, or from the reference or current time in the case of the Pasch. Now currently, or up until recently, the Laspers index was used for the CPI of the United States. What is the problem with that? Well, one, what would happen if you used any other number? Key issue is that tax brackets are indexed to the cost of living. And entitlements are indexed to the cost of living. So if there is even a hair's breadth of difference between one index number and the other, it creates giant transfers of wealth. What happened in 1930 was that a fellow, to get the first Swedish Bank Memorial Prize, whatever they called that thing, Ragnar Frisch proved that if you took all of the axioms which Irving Fisher developed in the 1920s as reasonable axioms for an index number to follow, that there was no index number that could be constructed which satisfied even three of these basic axioms. So not only do you have disagreement, but you have a theorem that says agreement and resolution of the index number problem is impossible. Now, as an example, we can note that if the initial price vector equals the final price vector, the top four indices yield unity, whereas the Divizia index does not necessarily yield unity. That is an example of a discrepancy. So let's look at it slightly more closely. The Divizia solves the transitivity problem, whereas the Laspers solves the cycling problem. What's the cycling problem? You have some price, which is relatively low for some good you're consuming, only a small quantity of it times zero. And because the price is low and stable, you start building your life around it more and more. You develop a taste for Bordeaux wine because it's relatively cheap. Suddenly, the Japanese discover Bordeaux wine and the price climbs. It takes you a while to figure out that you're wasting money, so you start switching from Bordeaux over to California wine. Your consumption declines, and then the price comes down as the Japanese economy tanks. Well, what's happened? What's happened is that the Laspers index sees no good at the beginning, the same price at the end, and it shows no difference. What does the Divizia index see? During this period of time, it records no change in the price. During this period of time, it sees you as being hit with a price increase. It sees no change in the price, and then the price comes down, but you have no exposure. So the Divizia index doesn't yield unity. This is called the cycling problem. On the other hand, if I stop it right in the middle, and I ask, what happens if I multiply the Laspers index between time 0 and time 1/2, and time 1/2 and time 1, what happens is that that's not compatible with going the whole distance from 0 to 1. Whereas in the case of the Divizia index, it behaves well under composition. So you see that this is the kind of conflict that Frisch was trying to look at. How do we try to see where there might be opportunity for us? So we start looking back at calculus, in the most basic form of calculus, calculus 1.0, if we think about it in terms of releases. You're in the XY plane, and mathematics is only reasonably effective because we've become quite jaded about applications in calculus. If I tell you that I have a way of maximizing the volume of water in a pool subject to certain constraints and I'm using calculus, you're not going to object that calculus was developed for celestial mechanics and shouldn't be used to figure out an optimum pool in someone's backyard. We're all used to this idea. Why? Because the x-axis and the y-axis in standard calculus are measured in real numbers. We're all comfortable with real numbers. We have a guaranteed notion of horizontal. And the idea of taking tangents by now seems quite natural. Now, it is odd that mathematics, which finds complex numbers natural, and physics, which finds complex numbers natural, are still relatively distinguished in that most fields do not force people to see a single complex number at any time. So the reals are very important to the story. So let's look at calculus from the point of view of a software company, where we're going to issue upgrades. So we have the original differential calculus, and we have multivariate calculus, which I'm going to call 1.1. We then have the absolute differential calculus of moving frames, and we pick up a major client with work of Einstein and Grossman and company in general relativity. And we go to covariant differentiation, in which we have internal quantum numbers, internal symmetry groups, and Yang-Mills theory, which extends E and M to the other remaining forces. And finally, we have some sort of gauge field theory in which we have function spaces, and we are no longer in finite dimensional territory, but we are frequently in infinite dimensional territory with infinite dimensional groups. Now, to some extent, some of these things make us feel that mathematics and physics are really special. For example, if I tell you that diff S1 has an important and distinguished role in economics, that's a bit of an eye-opener because many of us think that's the kind of a group that you're only forced to deal with in something as crazy as string theory. But hopefully, I can convince you that it's not entirely unnatural. So the mystery here is that natural examples of fiber bundles are ubiquitous. But they're ubiquitous within the areas in which we're used to finding them. And they're all but undiscovered elsewhere. So we have to ask ourselves, is the implication that mathematics and physics have a special relationship? Or is the implication that we have simply failed to follow our forefathers and foremothers in finding high-level applications of what should be relatively universal gadgets. So the question is, do other important examples simply not exist? And are these concepts like vector bundles or internal symmetry groups and quantum numbers emergent, or are they really truly fundamental and basic? And so hopefully, by trying to get a feel for the answers to these questions, we might actually shed light back on something as fundamental as theoretical physics. So first of all, let's think about gauge theory as calculus on fiber bundles. First problem is, where am I going to find things that look like space-time? Nice manifolds with good properties, not necessarily coordinatized. That's not so hard. We see examples of that in multivariate calculus. Where am I going to find interesting fibers? The fibers that we get to deal with in physics are truly interesting, and some of them in mathematics are very interesting as well, even mathematically distinguished so that you have sporadic and exceptional phenomena. The other part is that we have to figure out what's going to determine the horizontal. Connections aren't interesting unless, at some level, they're non-trivial. Rather, they're not interesting beyond standard calculus unless they can be non-trivial. So we have to imagine what it is that's going to pick out interesting connections. So in this talk, I'm going to be talking in more of a Levi-Civita context in which the truly interesting connections are going to be God-given, given some choices of structure. But the next step is to find connections that are given by equations and set dynamically. All right, so what is the plan? The plan is that we're going to try to take over all of economics by going to the heart of the matter. We're going to look at the most basic theories, and we are going to try to see if we can upgrade them. Now, what happened years ago is that marginalism swept through economics. What was marginalism? It was the introduction of the calculus into the analysis of market behavior. So if we have an upgrade of the calculus, there's nothing to suggest that we mathematicians and physicists can't swarm into economics and rip out every place that they've got one of these old-fashioned calculus machines and replace it with this new thing to solve problems that they haven't been able to solve. So that's the plan. I think we can take these guys. That's my feeling, and I could use your help. All right. So what do we have? We have to understand how they see the world. So how do they see the world? Well, they've got these vector spaces. Very often they throw away everything outside of the fundamental quadrant where all entries are positive. They foliate. So there is usually a foliation by hypersurfaces of codimension 1, which are convex to the origin. That will be called an indifference map. I will denote by O an element of the space of all indifference maps. There's some niceties here. They don't like local minima and maxima. They like this to be ever increasing as you go away from the origin. So they call these things bliss points. So we're going to foliate this positive ortho by indifferent surfaces. And then we're going to look at the inverse images given a particular choice of price for every value of the currency in which we are denoting the prices. These are called budget constraints. So the space of budget constraints are affine hyperplanes of codimension 1, translated from the origin, which are all based on the kernel of the pricing vector.
Before you go on, for us, I've seen vectors. So the indifference curve is a measure of a preference that some person has for eating chicken or beef or something.
Right. Which is not due to my insensitivity given Lee's dietary restrictions, but the Boskin Commission chose chicken and beef as an example of why people buy different quantities of different things. As the angle of the budget constraint changes, what happens is that people buy different quantities over here, trying to maximize their utility to get onto a higher indifference surface, expending their budget constraint. We're going to get to this in a second. What was interesting is that the Boston Commission could not identify any other reason why people would switch away from beef to chicken other than as a response to changing prices. And that becomes an important part of our story. So what leaves after here is what, in biology, they have this great term, the central dogma, as to how DNA codes for protein. And there is a central dogma in this story, which is that people buy the unique basket whose tangent at the basket to the indifference curve, whose tangent space, is equivalent to the kernel of the pricing vector in force. They wouldn't say it like that. So the idea is that the inner product of the vector with its dual expends the budget constraint, and they optimize by getting these subspaces to coincide. The space of all such baskets, given any particular level of expenditure, but with one pricing system in mind, is called the angle curve. There is no Marx curve.
Is that the same thing?
I don't think so. I'm pretty sure they would have driven it out. Okay. So this leads to the problem of the overstatement of the cost of living. And you want to talk about an expensive problem, it's a good one. What happens if you consume at point A under a pricing regime that gives you this angle? Right? You've got a budget constraint going through A. Suddenly prices shift. If you give me the money that I used to previously spend on my basket at A, am I going to buy A again? No. What basket I'm going to buy is going to be basket C, because that gets me onto a higher indifference surface. I'm expending the same amount of money. So if you compensate me based on repurchasing my basket under the Lust Pairs Index, I'm going to make myself much better off. And what you should have done is compensated me relative to basket B, because I get a savings from being able to substitute. So you only have to adjust me here in order to keep me at my same level of quality of life.
Just as these curves are equal amounts of happiness, roughly speaking. More happiness is that way.
It sounds dorky, but it's exactly the way they think about it. So the idea is that they talk about bliss and happiness and utility, and they used to talk about it in terms of utils, right? If you remember John Stuart Mill. So the idea is that once upon a time, we were imagined as to be giving off, you could measure by the angle of the corners of my mouth how happy I am. And then you write these things down, and you try to keep me at that level of utility. But a guy named Pareto decided, you know what, this is very silly. We can't measure this kind of psychic happiness. We don't have functional MRI yet, back in the early part of the century. So what we're going to do is we're going to throw away the cardinal labels, and we're going to be left with these ordinal utility functions. In other words, we're forgetting the cardinality and just keeping the foliation. So as Lee points out, this is a constant level of happiness, or a level of indifference, hence the name indifference surface.
But the distinction between being at A or being at B on the same curve means I could have spent so much chicken, less beef, or more beef, less chicken, I'm just as happy.
I'm just as happy anywhere on that curve.
But if I get more money, I'm going to jump up to where curve C is, because I want more stuff.
You want to make yourself, it's not necessarily even more stuff, it's that combination gives me more happiness. No, I mean, because you have sometimes you have less, they're very funny effects that I don't want to get into.
But having more money means I can go to a higher curve further up.
So there's a rule that says it has to be increasing with respect to the origin so that more money never makes you miserable. Whether or not that's true in the real world, I leave to you. So this cost of living overstatement is what concerns many people because of the sheer magnitude of it. What do I mean by that? It's a good paragraph to read, because if we can solve this and we can have any impact, it's probably worthwhile. The upward CPI bias by itself would constitute the fourth largest, and this is US, federal outlay program, behind only Social Security, health care, and defense. That is, the CPI problem would be the fourth largest program, if such a thing were considered a program. So any improvements should be welcome.
Just to restate it, so the problem is that real people will go along the present difference curve to save money, but the consumer price index is computed under the assumption that they won't do that, and they'll therefore increase their happiness at the same budget level.
It's disgusting, isn't it? But that's exactly right. They are going to go off and take the money that we paid them to buy their old basket, and as soon as we turn our backs, they're going to go and buy a completely different basket, making themselves better off. Also, the indexing of the tax brackets enters into the picture. So those are the two effects that really get you into big money. So it's the fact that the economy is hooked up to this number in such an intimate fashion that really causes the expenses to add up. So now we have a problem. If we're going to use indifference curves rather than just this mechanical index number that we were looking at before, like the less pairs, we have to ask, is it realistic? Now, what happens if we try to incorporate changing tastes? Right? What if my tastes don't remain stable over a 4-year period? So the famous question, are you better off now than you were 4 years ago? Try asking an economist that question with the idea that tastes may change during the period in question. What's the problem? Well, if at time 1, point A and point B leave you indifferent, and at time 2, your tastes have changed, so that this new curve intersects B and C, then B and C leave you indifferent at time 1. But point A is clearly less than point C because they're collinear. So you start to get into all sorts of problems of logic as you allow these curves and surfaces to cross. Now, what is the defense mechanism of a field that knows where its vulnerabilities are? Well, look at this definition from Becker. Gary Becker, who I've never met, but I do think about him a lot, is very famous for trying to make sure that no one ever raises the issue of changing tastes. This is why I need your help, because Gary likes to collect shiny medals, and it's very hard to unseat the Chicago school. But what I'm hoping to convince you of is that this school is so silly with respect to this as to render the theory really unusable. So he says, the combined assumptions of maximizing behavior, market equilibrium, and stable preferences. So he's encoding stable preferences which don't shift into the very definition of economics in an attempt to spike out this problem. So the most famous paragraph on this, I'll let you read it so you don't think I'm making it up, and I won't editorialize. It's really that way. McPherson's point of view is more sympathetic, but very much the rarer point. The problem with changes of taste have remained central and largely unresolved for 2,500 years, no doubt, making some economists think it is wise to define them out of the discipline at whatever cost in realism and relevance. Now, the real problem, which I'm hoping to convince you of, is that they don't have the right mathematics to look at the problems, and that what they fear is that this is going to bounce them out of relevance in making policy prescriptions. But what they really don't understand is that they've done a pretty good job, and that they're fearing that someone is going to introduce this problem without introducing the appropriate tool. So we have to ask, what would a solution mean? So you have preferences at period 1, and you have preferences at period 2. And again, we're going to take the Boskin Commission's idea that the only reason that you would change your chicken and beef consumption couldn't possibly be because you're now health conscious and you're cutting down on red meat. All it can be is that it's coming from a price change. Well, we're going to say no. That could possibly be coming because of shifting tastes. And so we're going to allow any two maps that fit this description. And what does it mean to solve the changing preference problem? It means to find a mapping of the set indexing the foliation at time 0 to the set indexing the foliation at time 1. without essential reference to utils. If you allow me to label these things by numbers, then I ask, what's wrong with saying, hey, curve B makes me 7 utils happy, and here curve D makes me 7 utils happy. So I'm going to call those curves to be in correspondence using the labels. So this requires an intrinsic way to match curves on the left with those on the right without using numerical cardinal labels. Okay. So, this is the eraser?
There is an eraser, no, right there. Right there,
Next to the
sorry.
left hand.
Yeah. But we also
Okay.
we have
Perfect. Okay. So what I'm going to try to do is to show you that we can solve the index number problem, and the changing preference problem, and the CPI overstatement problem using gauge theory. So that's the game. In order to do that, I'm going to introduce 3 vector bundles. No, I'm going to introduce 3 bundles, 2 of them vector, 1 of them principal. And I'm going to try to show you why I believe that this is the right way to go. So let's begin with the less pairs index. P1 dot Q naught divided by P naught dot Q1. Q naught. There we go. All right? So I'm looking at prices at time 1 over prices at time 0, and I'm using the reference vector from time naught to weight both of them. Now, I should point out that to every price index, there is a sort of dual quantity index. In this case, it's going to be P naught Q1 over P naught Q naught. So this is the price index, and this is the quantity index. Both of them lost pairs. If I did the posh, I'd be using current time weights. Okay? Now, what's wrong with this to a gauge theorist? What's wrong with those to a physicist? The key problem here is, what is this thing here doing at time naught being multiplied by something at time 1? How did it get from one place to another? Well, we parallel transported it using some kind of a trivial connection. Why use a trivial connection? Doesn't make sense. We have to find the economic connection. So here goes. So what I'm going to try to do is I'm going to try to give you theory 1. It's going to be based on a base space, which is going to be V cross V star minus some kind of a singular set. Namely, those combinations in which V, a vector in V and a vector in V star annihilate each other, right? What is my fiber going to be? My fiber is going to be V cross V star. My total space, the trivial bundle. Okay, what connection do I start with? First connection I start with is the trivial connection. But what happens to this bundle, F1, sitting over this space? It admits a decomposition into subbundles, right? So the idea is I've got, inside of V, I've got my vector Q, and I've got my n minus 1 dimensional subspace, ker P. So I've decomposed V into a 1-dimensional and n minus 1 dimensional subspace. Same thing is going to happen in V star. Economists have names for these things. They don't think of them in the same terms we do, but they call this the income effect. And they call this space the substitution effect. So far, I haven't added anything that they don't give you already. You're already looking at baskets, and you're always looking at prices. So what's the real connection that I use? Well, the real connection that I use is going to be the sum of the projection. So if the fiber decomposes as the sum of subspaces, let me call it E for effect, I equals 1 to 4. If the fiber decomposes, then I pre and post multiply by a projection map that I'm given the trivial connection. So I sum that up. Now, income effects are not mixed with income effects, nor substitution effects with substitution effects. Same thing in the dual space V star. I compare income with income, substitution with substitution. I have a notion of parallel translation. I then attack these indices, and I make sure that I never multiply something across time without transporting it properly. So if I want to use Q naught as a weight, I take the value of the vector P1, I use the economic connection, and I parallel translate it back. So the idea is that I use the parallel translate from time 1 to time 0 using the economic connection. What happens to the index numbers? They all become coincident. Go ahead, John.
So what's this 1 through 4? Is that an example of something? Or
No.
4? What are these for?
I've got two vector spaces, V and V star in the fiber. Let's look at V first. If you'll allow me that the point in the base space allows me to decompose into a one-dimensional and an n-1 dimensional complement, that's 2 of the 4. The fact that it occurs in the other is the second 2 of the 4.
And then my next question is, can you try to explain in a more intuitive way what this economic connection would be doing? So you're moving around in this space, basically V cross V star, in the base space.
Right.
So that's like changes in pricings and changes in quantities, and then you want to be able to lift that path up to this little space. But can you say that lift is like what someone would do?
So the idea is, I'm going to allow the modernization of the vector. If I'm looking at what I purchased in 1960 compared to what I purchased in 1990, I'm going to modernize the vector in terms of the ratio of the components purchased. But at each point in time, I'm going to say, to preserve the proper notion of length, let's say, I'm going to only allow it to change by economically allowed substitution effects. So I'm only going to allow the vector, I'm going to tell it to modernize properly, so that if I was buying an abacus in the year 0 and I'm buying a computer in the year 2000, I have to cut down on my abacus purchases and move towards computer purchases. But at each point in time, as I change my consumption pattern, I'm going to only do it by a substitution effect, so I never add value at any moment or lose value at any moment.
I don't know what a substitution effect really is.
If you're buying a small quantity of California wine and a large quantity of Bordeaux, right? And the idea is that you want to move towards California wine, but you don't want to change your total wine purchase. That would be a substitution effect. The amount that you increase your California purchase will be the amount that you decrease your Bordeaux purchase at current price. So substituting at any given moment is clear enough. What this says is, at each moment you're allowed to substitute to modernize the vector, but no other operation is tolerable.
And in the decomposition of those subspaces, you wrote little q. Is little q q naught?
Where did I write little q?
Right there, beside your left right hand. Up, right there.
Yes.
What is that little q relative to q naught or q1? Or it's q. Oh,
It's q an element of v. It's whatever basket I'm looking at.
So it's going to go from q0 to q1.
Yes, it's going to be there's going to be a path.
There's going to be a path, and that vector starts at q0 and ends at q1.
Right. There's going to be some path. Oh, hang on, John. There's going to be some path in the base, and there's going to be some vector mirroring it in the fiber. And it's going to be allowed to change by substitution only.
That's a choice you make to define theory one, is it?
Yeah, it's not much of a choice in that it's God-given structure, and the idea is I don't want to confuse income and substitution. Any economist would say that's a perfectly fine thing to do. Where they're going to choke is that this doesn't have curvature equal 0. So they're going to have to come to grips with their fears of holonomy. Holonomy is a great thing. We know that. They don't, but they will. Okay, so that's theory one. So hopefully the idea is that that looks to be reasonably natural. What does it produce? It produces the Divizia index. Everything converges to the Divizia. So in 1925, without understanding the proper context, these guys came up with the formula. No chance in the next example. Why? Because we're in the abelian finite dimensional case.
You're saying less, how is that, less pairs?
Less pairs?
The less pairs index, when properly made gauge covariant, becomes the Divizia.
Yes, as does the Posh, as does the Tornquist, as
They
the
all
Walsh. They all do. So now the point is that you get a perfect collapse, and you say, I wonder what this Divizia is, because before we thought it was illegal, and that it had the worst problem of all. Right? Okay. But think about flat Earth. Right? When somebody tells you that it's, they've got a direct route that appears to go over the pole, it looks pretty silly if you do it on a Mercator projection. So there's something to get used to, but once you get used to it, the hope is that you'll see that it is economic, and it gives you extra information if you want. Case 2. Finite dimensional, non-abelian. What happens in foreign trade? People disagree on the value of something between two countries, often with two different currencies. So now the idea is that we have QA and QB for two different countries. So my imports are your exports and vice versa in bilateral trade. And we have two different pricing systems, PA and PB. If the currencies don't agree, because purchasing power parity holds even a little bit imperfectly, and if our imports and our exports don't agree or are not valued at 0, then what we see is that we get complementary subspace, but this time 2-dimensional and n-minus 2-dimensional. So the picture is going to go through more or less exactly the same. The base space in this case is going to be V cross V star cross V star minus the singular set. The fiber is going to be V cross V star cross V star. The total space is going to be trivial. The connection is going to proceed in exactly the same way. You're still going to have 4 subspaces. You're still going to have projection operators. And what you're going to get is going to be, instead of the usual Divizia index, which is the exponential, and I'm going to write it a little bit funny here, PQ inverse, because I'm going to put P and Q, QA, QB. So these are two vectors. I'm going to put them into a n by 2 matrix, and I'm going to take PA, and I'm going to take QA, and I'm going to put that into a 2 by n matrix, so that PQ is a 2 by 2. So I'm going to take the exponent of the integral over the path of PQ inverse times P dq but now I have a problem going to have to do some kind of a time-ordered product to get the exponential. Otherwise, I'm reduced to doing things over simplices. So the time-ordered product of this is going to give me a 2 by 2 matrix, which is going to be the matrix value version of the less pairs in the Posh index. Again, economics has never seen these 2 by 2 valued indices. But the idea is that we're now in GL2R. And GL2R is intrinsically non-abelian, so we can't get away with the simple exponent that they were able to do in the abelian case, more analogous to electromagnetism. Now we're in something like isotopic spin. We've got non-abelian aspects, and then we now need a time-ordered product. The last example.
Just a question. Is this roughly the effect that if I have a chain of currencies,
Yes.
and I trade one for one for one for one for one for one, you're not assuming that you get back to the same place?
Well, if you're able to do it fast, and you can get spreads to zero, for example, by using EBS trading system, I mean, things get really tight. So if you can get your spreads to zero so that your transaction costs are low, and you can execute in milliseconds, and you can get what they call choice pricing, and then the bid and ask are exactly the same, you shouldn't be able to make money or lose money on that bet. So that is sort of a primitive man's notion of holonomy. But we'll see where that, hold that idea because it's coming up if I can just beat the clock here.
Sure, but holonomy is when you do make money.
Holonomy is when you do make money. Holonomy is a beautiful thing, but holonomy can cause you to lose money. Okay, last one. So this is supposed to be a really different example. So now we're going to do infinite dimensional diff S1 orientation preserving diffeomorphisms of the circle, and small change, I'm going to fix a point, so it's really diffeomorphisms of the real line. So infinite dimensional non-abelian. Now we're not going to see a vector bundle. We're going to see a principal bundle come out of nowhere. What is my base space? My base space, I'll put a hat over it because I'll change it in a second, is going to be the space of all ordinal preference maps, suitably topologized and made continuous differentiable. What is my group? My group is just this diff and what is my space? The space of cardinal utility functions, familiar from Mill. All right? So I have a preference map. And as long as I decide that their cardinal utility functions over it are surjective onto the positive reals, then the idea is that I can come up with different cardinal utility functions whose contour maps are indistinguishable when viewed over the space of goods and services. So these cardinal utility functions, these surfaces above the ordinal preference maps, as long as they have the same contours, I can act on them if the action is surjective, if the functions are surjective onto the reals by the reparameterizations of the reals that are orientation preserved. When I quotient out, what do I get? I get precisely the ordinal preference maps of Pareto. Okay, what does this buy me? Well, let's assume that I'm in this crazy infinite dimensional function space bundle, and I've got these groups, and I look for this path, and I look for a lift. Any lift, doesn't matter. That's looking for a time-dependent cardinal utility function. C of t element of the cardinal utility function. Now, what if I have a connection? If I have a connection, I could use the distinguished path. I could project down, and then I could lift it back up using the distinguished path to some other lift, which would be God-given except for the starting point. Right? So if I can measure how much I have to adjust this cardinal utility function to hit the horizontal lift in the connection, that is going to give me a very essential object. Why? Because if I scale the entire cardinal utility function, it's not going to have any impact. In other words, if I have a cardinal utility function at time 0, right? I compose that with, I'm not good at drawing upsilons. I forgot what I called it recently. Upsilon. And I compose that with a time 1 cardinal utility function. And this is based on doing a computation to bring the whole picture to be the horizontal lift. So I pick any time-dependent cardinal utility function. I adjust it by this object. And I map into the utils, I reparameterize the utils, and I map out. That operation is insensitive to the initial choice of cardinal utility function that was lifted above the space of ordinal maps, which were actually chosen by our consumer. So this gadget is a solution to the changing preference problem. All right, and notice, these are all objects. These two objects are the center of their theory. And this object, who can object? What do we get if we use this intertemporal welfare comparison? Is we get a consistent notion independent of the choice of cardinal utility function representing. Well, we don't have a connection. In fact, I conjecture that there isn't a natural connection on this space that's distinguished. Very sad. Except, I have prices. So if I Cartesian product with the space of prices, this becomes my true space, B3. Theorem, there exists a God-given connection on this total space. Prices are available in the market, so I'm not adding any new information that wasn't available otherwise. And now I've solved the changing preference problem using gauge theory with nothing that these guys don't use themselves. What I ask you as physicists, aside from your help in overthrowing Chicago, is to try to ask the question, what does it mean if all of this natural structure is just outside our door for our own theories? Does it mean, we know that no deity created these markets, and yet the fit is as hand in glove to my way of thinking as it is in the standard model. So what we're discovering is the unreasonable effectiveness of utility as a gauge theory. We have a fiber bundle, which is cardinal utility functions cross prices. We have honest-to-God curvature. We have a solution to this problem. And this gives us a Rosetta Stone. Namely, we have particle theory, we have economic theory, and we have geometry. And I would conjecture that this story does not stop here. Why? Because what we're looking at is the fact that it's not that particle physics and geometry have this peculiar relationship. It's the fact that we have started having a problem finding applications outside of what it is we do. And to go a little bit farther and more provocatively, I would say that we're having a problem with our monastic culture integrating the talent and the understanding that exists in theoretical enclaves like this one, with the real-world problems right outside our door. And this is leading to a distorted way of thinking about theoretical physics and mathematics as well. So the key question is, what does this tell us? Does this tell us that geometry is emergent? Do connections, are they fundamental? Are we looking at effective theories? Are we looking at basic theories? I think that as we find more applications, this is going to look more commonplace. And Lee has asked the question in a paper about why are there no Einsteinians? Well, in part, the fact is that we haven't been applying the tools of the trade successfully outside. If we start to do that, the picture may look very, very different. So just to give you an idea of the formulas, what I was calling upsilon here, I think is omega here. I did not have the time to get this in the form I wanted before the talk, so forgive me. But the idea is that it's just going to be some sort of Dyson form of a perturbation series, which gives you this adjustment factor. We have this construction of the changing preference welfare map. We have a bilateral index, which you can compute with no knowledge of preferences from the assumption of Cobb-Douglas preferences. What is that? You take good 1, raise it to the A to the alpha power, good B, you raise it to the beta power, and you raise the last one to the 1 minus the sum. So there's a canonical change, preference map when you don't know what the answer is. And so you can interpolate between two observed purchases. Somebody purchased something at time 1, something at time 0. You assume Cobb-Douglas preferences, interpolate, and you get another index number based on the changing preference. So this is as concrete as you please. And lastly, we have this trade index, which is a 2x2 matrix-valued object coming from a non-abelian theory. So in closing, I was once told by someone that the Chinese, and I don't know why the Chinese get credit for all these things, say that if you're going to try to see the universe in a single grain of sand, make sure the grain of sand is well chosen. I think there are a lot of things to see here. And one of the things that would be terrific in conversations, I'm here till Friday, is to find out whether there's interest in taking the tools that are common to our stock and trade here and heading into the markets and taking it at sort of a different point of view as to what geometry and physics are really doing together. I thank you for your time.
Questions, comments? Mr.
Connor? In the change from constant preferences to changing preferences, it appeared to me that the number of products available are constant. In other words, chicken beef goes to chicken beef, but the curves are different. Is it possible to incorporate if you suddenly tomorrow have 15 more choices than you had yesterday?
Great question. Yes, it is, but it's not as beautiful as you would like. So one way to do it is to throw all the goods and services that will ever be available and impute phantom prices that would drive their consumption at technologically unfeasible ages to 0 or near 0. So the idea is, yes, there's a toaster available to the infant Jesus, but unfortunately, the price would be prohibitive. That's one thing you can do. Another thing you can do is you can work with hedonics. What is hedonics? It is the mapping, again, they wouldn't say it this way, of one vector space to a vector space of strictly smaller dimension with non-trivial kernel. So the idea is that a toaster becomes a food preparation device, and a skillet at a different period of time would be equivalent to a toaster through their efficacy in making toast. I leave it to you. But there are ways of incorporating it. My goal is not to solve the problem of how to get a toaster to the infant Jesus. It's to try to figure out how to expand the framework well beyond where it is already.
Taking a quick look at the map, you had, I'm not sure how seriously you meant all the rows and columns. Like you had the Ihara-Foam effect
Yeah.
as an analog of the cycling, what is it?
Cycling problem?
Cycling problem. And so that's, I was trying to figure out where the quantum versus classical theory here. So that's quantum.
You know, I didn't show that, and that's a good thought. So, where am I? Okay. So here's a picture. This is Lee's question. Is holonomy good? Is holonomy bad? Why should we accept it? I'll get close to our bosom. So you have a situation here in which I'm going to depict graphically the one-dimensional fiber bundle. Assume two goods, right? If I'm going to quotient out V cross V star, I'm going to have a four-dimensional space, but I really only need the relative proportion. So I'm going to quotient out and work with projective spaces in my base space. So that's going to allow me to get into visual territory without loss of generality. And then I need a one-dimensional fiber, which is just going to be the income effects, and forget the substitution effects. So here you are in price quantity space, where prices, let's say, are exhibiting simple harmonic oscillation, right? We have 3 hedge fund managers. So we have manager 1, whose divisive price is 2. His divisive quantity is 1/2. We have manager 2, whose divisive price is 1, and whose divisive quantity is 1. And we have manager 3, whose divisive price is 1/3, and his divisive quantity is 3. All right? So they've been in the same market, and they wound up their position. They had the same positions that they were given, and they were told on December 31st, get back to the same relative components that you started the year with, and we're going to evaluate it. Now, what do you do with these 3 guys? First of all, he gets fired. So why are you guys going to fire him? Well, he sat on his capital. He didn't do anything. In the aggregate, his quantity index stayed the same. What are you going to do with manager 1? With manager 1, if he hadn't brought in any capital, so he had no subscriptions, and he hadn't lost any capital because his investors wanted it back, so he had no redemptions, he would have gone around this loop, and he would have come back, if he'd been successful, with a higher quantity. But he came back with the same composition. So if all of these guys had P naught equal to P1, I guess I forgot this part, my mistake. These should be little. Okay, so all 3 of them had their initial price vectors and their initial quantity vectors equal. The only way that this guy could have come back with a quantity index of 1/2 and come back with the same quantity that he started was he was successful in attracting capital. He's what we call an asset gatherer in the hedge fund industry. But he's lost money in trading. So what you now do is you take manager 1 and you make him the sales rep for manager 3, who is some kind of a misanthrope who's very good at trading markets. But boy, do people take their money away from him as he's making their money, because he only ended up with the same quantity that he started with by virtue of the fact that he went around the loop and people took the money away in redemptions and said, I can't deal with that guy. So the idea is that everybody started with the initial prices the same, everybody finished with the initial prices the same, started with the initial quantities the same, finished with the final quantities the same. And yet the Divizia index gave us true information about what happened in the system. Why? Because the holonomy is a good, positive, healthy thing that is naturally present in the system. There's no sense in flying from London to Los Angeles on a direct route via Mercator projection. You should use the pole. So at some level, the cycling problem is no problem at all, just as the way the Bohm-Aronoff effect is a real feature of the world and should be embraced rather than feared.
Okay. Other questions?
I hope you guys will drop through. I think I'm in 259, if anybody wants to talk.
Great. Well, let's thank you.